Lesson 7, Graphing Cosine and Sine Functions. In this section, we are going to be taking both the functions sine and cosine and graphing them as functions of x on the Cartesian or rectangular plane. This is going to be different than what we did where we related sine and cosine to points along the unit circle, because in those cases, we were considering sine and cosine as functions of a rotational angle measure. In this case, what we are plugging into sine and cosine are values along the x-axis. Some things about the graph of sine and cosine that we are going to see here. Firstly, is that the graph of y equals sine of x is considered an odd function because it is symmetric about the origin. Whereas the graph of cosine is actually considered an even function because it is symmetric about the y-axis. Functions such as sine of x and cosine of x are known as periodic functions, which is when there is a real number p such that f of x plus p is equal to f of x for all real numbers of x in the domain of f. That smallest number p, if it does exist, is called the period of the function f. What it means to be periodic essentially means that the function will repeat itself after some period of time. This is going to be in stark contrast to many of the functions established in algebra courses, as many functions there do not repeat themselves. However, that is going to be a very common concept here in trigonometry. In order to come up with the graphs, however, of both sine and cosine, let us first establish a few points that we can use for that. The points I'm going to establish are going to be from using the quadrantal angle measures 0, pi halves, pi, 3 pi halves, and 2 pi from the unit circle. At those angle measures, sine and cosine, or the y and x coordinate in the unit circle, starting with 0 radians, sine of 0 radians is 0, whereas cosine of 0 radians is 1. Sine of pi halves radians is 1, and cosine of pi halves is 0. I am using these points here on the unit circle. If I continue using this pattern at pi, sine of pi is 0, cosine of pi is -1. At 3 pi halves, sine of 3 pi halves is -1, cosine of 3 pi halves is 0. And lastly, 2 pi, which is the coterminal angle measure for 0, should have the same values as 0. So sine of 2 pi is also 0, cosine of 2 pi is also +1. Let's move into graphing now the graphs of both sine of x and cosine of x using these points. Here we are going to create the graph first of sine of x. I also have the table for x and sine of x given above, and we can use that to come up with the graph of it. Within that table, we will treat the x values as the x coordinates, and we will treat sine of x as the function y. The first point I will now plot then is 0, 0, which is at the origin. The second point I will plot is pi halves, 1, followed by pi and 0, 3 pi halves and -1, as well as 2 pi and 0. With these points, we can start to come up with the graph of sine. However, a very important concept of both sine, cosine, and all the other trig functions is that they are smooth, which means that I am not going to be connecting these points with a jagged line like this. What is happening with both the graphs for sine and cosine is that we have a smooth graph or a smooth function from one point to the next. And what we are going to create here, some know it as a sine wave. So for example, our graph for sine here is going to look like this. From 0, 0, we increase gradually up to the height of 1, and then we start to decrease back down to the x-axis, continue to decrease gradually down to the point at -1, and increase gradually again. If you would like to use other points from the unit circle to more formalize these points, such as using sine of pi fourths, which is equal to square root of 2 over 2, that means that you have another point at pi fourths comma square root of 2 over 2. However, what I have drawn here is not the complete graph of sine of x. We would consider this to be one period of sine of x, because all I have graphed are the angle measures from 0 to 2 pi. However, that is not the only inputs that we could have for the function of sine. We could graph and plug in other angle measures that go beyond 2 pi or beyond 0. And what happens with this, because it is a periodic graph, is that this graph repeats itself. So it continues making this pattern over and over and over again. At the point of 2 pi, that is where we start to see that periodic nature. This graph will increase up again to 1 and then decrease back down. Likewise, from 0 to the left, it will decrease back down to -1 and then increase back up. We're going to see this periodic nature to this graph of sine of x. Since we have the graph now, though, we should be able to establish both the domain, the range, and the symmetry, as well as some other information for the graph of sine of x. The domain are the possible values of x that you may put into the function of sine. In this case, there are no issues with any angle measures that you can plug in for sine of x. So that means our domain is all real numbers, or sometimes also written as -infinity to +infinity. The range, however, is not infinite. The range is restricted to a point. The range are the possible y values that you get in return. Whatever angle measures we plug for sine, the maximum value of y that I seem to get is restricted up at +1, whereas the minimum value is restricted down to -1. This means that my range spans from -1 to +1 inclusive. So we write that with hard brackets from -1 to +1. This should also make sense if you recall that sine of x is considered the opposite over the hypotenuse. If you got a ratio that was larger than 1, for example 2, that would imply that the opposite side is 2 times larger than the hypotenuse side, and that cannot make sense within a right triangle. Lastly, we have the symmetry. We said earlier that the symmetry for sine is considered odd. The reason for this is because it has symmetry about the origin. If you take the graph of sine and you spin it around the origin 180 degrees, this graph will fall back on top of itself. If I spin this curve down 180 degrees and back up, it falls right back on top of itself, which means it has symmetry about the origin. In terms of other information for sine of x, we already have 2 of the pieces listed here that is considered a continuous and a smooth function. What that really means is that there are no breaks, no gaps, and no asymptotes within the function of sine of x for its domain. This comes more into play later in other mathematics, for example in calculus. However, another piece of information that we want to add to this is that the function of sine of x is considered periodic and has a period of 2 pi. We say that this graph has a period of 2 pi because that is how long it takes for it to repeat itself. For example, if you count from the origin point, I'm going to trace along this graph until it starts to repeat itself, and it does so once I get to 2 pi. At that point, that is where the graph begins to increase again towards +1. However, you can count the period from any portion of the graph. It does not need to be in the middle of it. I could count the period from the peak of the graph of sine and see where do I start to hit a peak again and decrease back down to 0. That will then happen next at 5 pi over 2, which is 2 pi away from pi halves. Either way, we have here graphed the graph of y equals sine of x. Let's move on into cosine. Cosine is going to have a lot of similarities with sine. However, the points that we are going to graph are going to be different. Again, I have the table for the x and y values that we are going to be graphing, the x values being the inputted angle measures, the y values being the output from cosine of x. Our first point we will graph is 0, 1, which puts us 1 high on the y-axis. Then we have pi halves, 0, which puts us on the x-axis. Pi, -1 puts us down here. 3 pi halves and 0 puts us back to the x-axis. And 2 pi and 1 brings us back up to the top. Just like with sine, however, this is supposed to be a smooth function that's not supposed to have any sharp turns. So I am not going to connect these points like a V. Instead, in order to connect these points, I'm going to make a smooth curve from one point to the next. And it will make a very similar wave type of function. If I start from the top point at 0, 1, I will curve down gradually to the x-axis. Curve again gradually down to the point at -1. Back up to the x-axis. And back up to +1. This graph, also like sine, is going to be periodic, however, because the values that I can plug into cosine are not restricted to just be 0 to 2 pi. I can graph and plug in angle measures beyond both 0 and 2 pi, and find that this graph continues its periodic nature beyond this point. With this graph created, we can now establish the properties. The domain of cosine is going to be the exact same thing as the domain for sine. There are no restrictions for what angle measures I am allowed to submit inside of cosine of x. So it is also all real numbers, which can also be written as -infinity to infinity. The range is also going to be the exact same thing as sine. The range is also restricted for the y values from -1 to +1. This should also make sense because cosine is considered the adjacent over the hypotenuse in a right triangle. If, say, cosine of x equaled 2, that would imply that the adjacent side is 2 times larger than the hypotenuse, which cannot happen. So we have our range is also going to be from -1 to +1 inclusive. However, not all things are the same for sine and cosine. The symmetry is going to be different. The symmetry for cosine is actually going to be even. It does not have symmetry about the origin like sine does. If you rotate this graph about the origin, what you will get is actually this instead, which means that the graph will not fall on top of itself. Instead, the graph of cosine has symmetry about the y-axis. If you take this graph and you flip it across the y-axis here, you are going to find that any point is just going to fall back on top of the same graph here. And that is going to hold true for any point within cosine. For the properties, yet again, it is continuous and smooth over its entire domain, which again means it has no breaks, gaps, asymptotes, or anything like that. And also, it is periodic, and it has a period of 2 pi, which means, just like with sine, it takes a distance of 2 pi along the x-axis for the graph to begin to repeat itself.